Okay, hi. So today we're gonna talk about sufficiency. If you're watching this video, you're watching about sufficiency. Notice this new notation. We're using this little vector. I'll put this little arrow over just a y to represent the whole sample. Same with little y. dn is just a arbitrary general notation. Okay. So we say that if we have a sample that's IID and has a parameter theta associated with the distribution of yi, then a statistic t of capital Y is sufficient, which I'll abbreviate like this, SUFF, for theta if, and we'll do two cases, discrete and continuous. So for the discrete, it would be if the probability I could put anything here, but you see that if y is going to be equal to little y, then t of capital Y has to be equal to t of little y. So this is the only possible value for the statistic if this condition is going to be true. So probability the sample is equal to these particular numbers, given that the statistic is equal to this number. This is what we want to compute next. This is not dependent on theta. So this is the definition. So this is the discrete case. So let's see, then t of y is sufficient for theta if so is not a function of theta. So this is the discrete case, or the density, the conditional density f. Okay, this is the discrete case here, and then for respectively y discrete or continuous. Okay, so in other words, if we know the value of the statistic for the sample, we know the distribution of the sample conditionally. And we know it without as a function that does not involve the parameter. So in a sense, we've taken the parameter out of the distribution. This is about as good as you can do. And so sufficiency is a desirable property. It also corresponds to estimators that have low variance. Well, let's just do some examples now, see how this works. So example one. Suppose y is Bernoulli. We'll start with two discrete ones, parameter p, and show that if I take the sum of the sample is sufficient for P. Okay, so we just say probability given the sum well, if I use the rule here, and now you can see why I was able to just put this in here instead of a general value here. This is just probability y equals little y and the sum divided by probability. The sum is equal to this number, but the numerator I can take this condition out of the numerator because now it's the intersection of these two, and this is already included in this first part here, which is, now think about it, two vectors are equal, every element is equal. So I'm going to take this out and I'll rewrite the top. So this is the probability y1 I just took out the top. And for some reason, I rewrote the condition that the vector equals the little vector, just to remind you while the notation's new. Okay, so we know these in terms of P, right? IID. So the top is probability y1 equals little y1. Or let's say a general yi. I can write this as a product from 1 to n. So this would be p to the little yi, 1 minus p to the 1 minus little yi. You can convince yourself that's correct. And then for the bottom one, the sum of the yi's is a binomial random variable. So the bottom is just n. Choose the sum little yi. And right, and now I want p times the sum little yi, and I want 1 minus p times n minus sum. Right, okay, and multiply. When I multiply the top out, I get these terms in the bottom, right? So the whole thing is just equal to 1 over n choose the sum yi, which is not a function of p. In other words, if I know this sum, if I know the sum here, if I know the sum of yi, I know how many of the observations were 1 versus 0, then I know the probability of y being any particular sequence. So maybe we could do a little short example like that. So for a little example, for a little numeric example, suppose suppose we want, say, probability y equals, say, 1 1 0 0, given the sum yi equals 2. This is just 1/6. And you notice I did this without knowing p. Okay, I didn't ever specified p, and I was able to compute this probability. I didn't need p anymore. So if you know your sufficient statistic, you basically know all you need to know about p for this, for anything concerning, to compute these probabilities. So you can't do better than that, is the idea. Let's do another example. So for example 2, I'm going to do another discrete example. We have some continuous ones too. So suppose I have y1 to yn iid. We'll just go back and forth with the vector and the list like that. Is Poisson lambda. Then again, it's the same statistic. Then is sufficient or lambda. Let's show it. Let's go to this. Okay, so I'll just fill this in. It's just the product. Put in the PMF, e to the minus lambda. Over, now remember, if you add independent Poissons, there could even be different rates. You again get a Poisson with rates that add. So I have n of these lambda, so I have a new Poisson down here as PMF e to the minus n lambda. So the term out front, I must have n lambda here. And here I must have the sum. Right, because I'm adding them, and so the I'm adding the yi's here, and I'm saying that is again Poisson. So it's just Poisson with rate lambda, with rate n lambda. So I get n e to the minus n lambda to the sum of the little yi's, and then divided by the sum of the little yi's. Factorial, right? Well, you can see this will cancel here, this will cancel here. So we're done basically. So let's just write this out. This all cancels up here, right? So I just have on the top, I just have not very much, right? This comes up to the top, and this goes down to the bottom. So I just have the sum yi over on the bottom. I just have n to the sum yi, and I have times this stays, but I have the product of it, right? Yes. So I have the product of yi. Okay. Looks all right. Notice not a function of lambda. Maybe let's do a little numeric example again. Maybe that was helpful, maybe not, but let's try it. So for example, little example. Probability, say that y is equal to, I don't know, given the sum. You see why this has to be the sum of this, right? This can't be equal to this if the sum of yi is 4 or something. So those all have probability 0, so you can take those out. So this is equal to, just from probability, we get this, right? So this would be equal to 3 factorial. I have n is 3 and the sum is 3 also, so I have 3 to the 3, 27. And then I have the product of the factorials. That's just 1, 0 factorial, 1 factorial, 2 factorial. So that's just 2. If you want. And so you get 3, so you get 1, 9. I didn't need to know lambda. Interesting, huh? We never knew lambda, right? We never know lambda, but we know that probability. Okay, we next have this theorem. You notice both times we did not find the sufficient statistic. We were asked to show something was a sufficient statistic. So, what you want to do now is be able to find one. And this is also a more powerful method for proving something sufficient too. So let me stop and then we'll go to part 2 of the lecture.